The generation and storage forms of application data are diverse, relying not only on traditional relational databases, but also on various data sources such as NoSQL databases, cloud storage, APIs, file systems, etc. Integrating and analyzing these data faces the problem of mixed computing of diverse data sources. Logical data warehouses can facilitate multi-source mixed computing to some extent. As most logical data warehouses are based on SPL, RDB data sources can be accessed through table mapping, but other types of data sources are more difficult and require complex data virtualization technologies, which can only be partially implemented. Moreover, the logical data warehouse system is too heavy and often more complex than the application itself, making it only suitable for large-scale scenarios. SPL provides real-time mixed computing capabilities for multiple data sources, enabling mixed computing for any accessible data source. Moreover, SPL's multi-source mixed computing function is very lightweight and can be directly embedded into application programs for operation. SPL has two types of data source connectors, native connectors and external connectors. Native connectors, which are built into the SPL core system, include common data sources such as RDB, text, Excel, JSON, and other local files, as well as HTTP data sources. In contrast, external connectors encompass diverse data sources like MongoDB, Kafka, Elasticsearch, and cloud storage, which are not part of the SPL core system and require separate deployment. Unlike the mapping method used in logical data warehouses, SPL supports and encourages the use of native syntax of data sources for data access and computation. If the computing power of the data source is insufficient, SPL can supplement it, as will be demonstrated in the following examples. Here are some of the data sources supported by SPL, including most common ones. The external connectors are located in the external libraries, which serve as the extension libraries provided by SPL for specialized functions. These functions, which are not commonly used in general scenarios, can be temporarily loaded from the external libraries as needed. There are various types of external data sources, and not all are commonly used. Therefore, offering these connectors as external libraries provides greater flexibility, allowing for the timely addition of new data sources without impacting the existing ones in the future. The vast majority of external libraries are external connectors. SPL offers two types of data objects for accessing data sources, table sequence and cursor, which correspond to in-memory data table and streaming data table, respectively. Almost all data sources, including RDB, provide interfaces for these two types of data objects. Smaller datasets can be read all at once using in-memory data table, while larger datasets must be retrieved incrementally using streaming data table. With these two data object types, SPL can accommodate nearly all data sources. Unlike logical data warehouses, SPL does not require predefined metadata for mapping. Instead, it directly utilizes the methods provided by the data source to access data, as long as the data is encapsulated in one of these two types of data objects. This approach preserves the characteristics of the data source and fully leverages its storage and computing capabilities. Additionally, there is no need to perform any preliminary data import actions, as real-time access is sufficient. These two types of data objects represent the common capability of diverse data source access interfaces. In contrast, the mapping data table method employed by logical data warehouses fails to adequately abstract the common features of diverse data sources, highlighting a significant difference from SPL. Next, let's take a look at the specific usage. First, configure the most common JDBC connection within the IDE, using MySQL as an example. Configure the standard MySQL JDBC connection as illustrated in the diagram. To prepare external library, first you need to download the external library driver package from the official website, extract it, and place it in SPL installation directory. Click on the Tools menu in the IDE and select Options. Under the Environment tab, enter the path where you just downloaded and extracted the external library. You will see a list of all external libraries. Select the libraries you need to load. Here, we have chosen MongoDB. After confirming, restart the IDE for it to take effect. Our example originates from the e-commerce business and utilizes MySQL to store order-related information. The structure of the two tables involved, orders and order items, is as follows. These two tables are associated through order ID. Due to the dynamic nature of product information based on type, such as electronics having brand, model, and specifications, while clothing including brand, size, and color. MongoDB is used to store product information. The attributes field accommodates dynamic attributes, and the product collection is associated with MySQL via product ID. These are sample data in MySQL and MongoDB. We want to query the total sales of 3 product categories, tablets, wearables, and audio, from the past month, which will involve mixed queries across MySQL and MongoDB. Take a look at the SPL script. A1 connects to MySQL, then A2 queries the order data within 1 month using SQL. Option at X indicates closing the connection after querying. The query result is as follows. A3 connects to MongoDB. A4 uses the Mongo shell function to query and filter data, with the @d option indicating to return a table sequence. The function parameters or JSON strings conform to the MongoDB command specification, which is the native syntax of MongoDB. You can see that the data meeting the criteria has been retrieved. A5 associates the two parts through product ID, and this is the association result. A6 summarizes the order amount by product type, calculates the final result. The entire process of implementing the multi-source mixed calculation is straightforward. We will then use Kafka to participate in the calculation. When the user places an order, the order data will be sent to the order subject by the producer. Take a look at the producer script. A1 connects to the Kafka server, and the content of the property file my.properties is as follows. A2 is the order data to be sent, which is typically received from a transmitting program. We write it directly here. A3 sends the order data, and A4 closes the connection. Next, let's take a look at the script for consuming data. A2 retrieves consumer message records, and returns a table sequence, and the result is as follows. A3 converts the order data JSON string into a table sequence. A5 queries all product data. A6 obtains all information related to the order and product based on the association via product ID. At this point, the join calculation between Kafka and MongoDB has also been completed. When dealing with large volumes of data, full reading may be slow and may lead to memory overflow. In such cases, the cursor mechanism should be adopted to read the data gradually in a streaming fashion. Let's modify the previous example of MySQL and MongoDB mixed computing. A2 changes the original query to cursor, which returns a cursor object without fetching the data immediately. Using the @c option in A4 means that the queried MongoDB data also returns as a cursor, and the result is also a cursor object. A5 utilizes the join_x function to associate two cursors, which necessitates that both cursors be ordered by the associated fields. Consequently, we sorted them in both the SQL of A2 and the MongoDB command of A4. The associated result of A5 is still a cursor, and if fetch is used to retrieve data, the actual result can be seen to be a multi-layer table sequence. A6 summarizes by category and obtains the calculation results. It is only at this point that all cursor operations begin to fetch data and perform computations. Almost all data sources can use SPL cursor to handle big data calculations. Let's take a look at how to use SPL in an application. SPL is developed in Java. Simply import these two jars into the application, and then place the SPL configuration file in the application's class path. racksoftconfig.xml is the key configuration file of SPL, and its name cannot be changed. In racksoftconfig.xml, external libraries need to be configured, and you can configure whichever one that is used. At the same time, the MySQL data source also needs to be configured here, with connection information configured under the DB node. SPL is encapsulated as a standard JDBC interface, which can be accessed by loading the SPL driver, and then calling SPL script. This approach is consistent with typical database JDBC calls to stored procedures, so we will not elaborate further. The above is the content of SPL multi-source mixed computing. We have only demonstrated mixed computing with a few data sources here. However, SPL supports a wide range of data sources and can be extended further. Thanks to the provision of unified data objects, mixed computing can be easily implemented whenever SPL can access the data sources. SPL is an open-source software that can be obtained from GitHub.